Okay, let's dive right into this mystery. Listen to this first sentence. John took a train from Paris to Istanbul. He likes spinach. Now listen to the second one. Jane took a train from Paris to Istanbul. She had to attend a conference. Why does your brain completely reject that first one as a random, confusing jumble, while effortlessly accepting the second one as a perfectly normal story? The grammar in both is absolutely flawless. The vocabulary is incredibly simple. But with John and his sudden love for spinach, your brain is desperately searching for a connection. Is there a spinach shortage in France? The fact that we even try to make that connection reveals something profound about human language. Sentences just don't exist in a vacuum. They rely on an invisible underlying logic.
Welcome to The Explainer. Today, we're essentially stepping into the crime scene of language to reverse engineer the exact clues that make human communication actually make sense. We're talking about discourse coherence. It's the hidden architecture, the invisible glue that takes a random pile of sentences and transforms them into a captivating story, a persuasive argument, or an entire encyclopedia page.
Here is our roadmap for solving this puzzle together. We'll start by defining this invisible glue, map out those coherent relationships, learn how to parse the discourse structure, track how we maintain focus on entities, and finally, look at how modern neural networks handle it all today. All right, part 1, the invisible glue of text.
As humans, we process this glue holding our sentences together completely subconsciously. We just kind of feel when a text flows and when it crashes. But what's really fascinating is that the philosopher David Hume hit the nail on the head centuries ago. Way back in 1748, he pointed out that even in our craziest, most wandering reveries or in our very dreams, our imagination doesn't just run totally at random. He realized that there was still a connection upheld among the different ideas. Even a wildly loose conversation has a thread connecting its transitions. Hume was pointing out exactly what linguists today call coherence.
And a perfect example of this, what linguists call global coherence, is Orson Welles' legendary movie Citizen Kane. If you've seen it, you know it famously shatters the linear timeline. It starts with the main character dying, and then just bounces backward and forward in time through all these flashbacks. But we never get confused. Why? Because the underlying logical structure, the investigation into his final word, Rosebud, remains perfectly intact. The global coherence is absolutely rock solid, even when the chronological timeline is scattered.
Moving on to Section 2, Mapping Coherent Relationships.
So human intuition is great, but we can't exactly program a computer with vibes. We have to map these relationships out mathematically. Enter rhetorical structure theory, or RST. Think of it like mapping text as a solar system. In this model, you have a main sentence, which we call the nucleus. This is the core idea that can stand totally on its own. Orbiting around this nucleus are the satellite sentences. These satellites are less central. Their whole job is just to provide evidence, background, or reasons. For instance, if I say, Kevin must be here, that's the core nucleus. His car is parked outside is this satellite giving you the evidence. You can literally build massive, complex trees of entire documents just by mapping out these nucleus-satellite relationships. Now, another huge framework we use is the Penn Discourse Tree Bank, or PDTB. Instead of building a massive global tree like RST, this one plays detective on the ground. We call this a lexically grounded approach. It hunts for explicit discourse connectives, words like because, although, since, or when. These words are literally logical signposts on the highway of language. They tell the reader and the computer exactly how two neighboring sentences are supposed to relate. It maps these out pairwise, just looking at the immediate connections without worrying about the whole global document. But here's where it gets a bit tricky. What happens when those signposts are just missing? Let's look at this real-world example. First sentence, a politician is in a position to get somewhere with his agenda. The very next sentence, as a former White House aide, he is savvy in the ways of Washington. Notice anything? There is no because written there, but you instantly understand that his background is the reason for his current position. The tree bank labels this an implicit connection. Even without the neon signposts, the underlying logic is still gluing the text together. Okay, Section 3, Parsing the Discourse Structure.
All right, so we've got the theories down. The next step is figuring out how to get an algorithm to actually parse this structure. Before a computer can build any beautiful logical trees, we literally have to chop the raw text into usable puzzle pieces. Linguists call these pieces elementary discourse units, or EDUs. Take this sentence, for example. It's not one giant block, it's distinctly broken down. Mr. Rambo says is one unit, that a 3.2-acre property is another, overlooking the San Fernando Valley is another. Figuring out exactly where to slice these brackets is a massive technical hurdle, because if you cut the puzzle piece wrong, the final picture will just never make sense.
To solve this, modern natural language processing uses a neural encoder. It scans the text word by word and spits out a sequence of zeros and ones. A zero basically tells the system, hey, keep going, we're still inside the same puzzle piece. But a one? That's a signal to make a clean break, the start of a brand new structural unit. Once the neural network chops the text up into these EDUs, it passes them on to a parser to figure out how they actually connect, whether they're showing evidence, elaboration, or contrast.
Which brings us to Section 4, Tracking Entities in Focus. Now, logic isn't the only thing keeping a story together. We also have to maintain focus, or things get really annoying really fast. Listen to this version. John went to the store. It was a store he frequented. He was excited. It was closing. It's incredibly choppy, right? You're getting cognitive whiplash bouncing back and forth between John and the store. Now compare that to a much smoother version. John went to the store. He was excited to buy a piano. He arrived as it closed. So much better. A framework called centering theory explains why. That smooth version works because it keeps John as the highly salient entity, consistently keeping the focus on him. But how does a computer track this? It can't feel cognitive whiplash. Researchers need hard data. Take a look at this real-world sentence about a Justice Department antitrust trial against Microsoft. It is absolutely packed with entities: the department, the trial, Microsoft, the evidence, the competitors. As the paragraph goes on, how on earth does an algorithm know what to focus on? Well, researchers Barzilay and Lapata came up with a brilliant solution, the entity grid model. They basically turn the text into a spreadsheet. The columns represent the entities, and the rows represent sentences. The grid tracks exactly what grammatical role each entity is playing. Is it the subject, an object, or just totally absent? If a machine sees dense, solid columns of subjects and objects, it knows exactly what the story's about. But if a column is sparse and full of empty dashes, that entity was just a throwaway detail. By mapping smooth transitions, the grid can mathematically score how coherent a text really is.
Finally, Section 5, Neural Coherence Models. So all these theories are fascinating, but how do today's deep learning models handle all this without human-labeled grids or strict grammar rules? They actually train themselves. It's a technique called self-supervision. Using tools like a local coherence discriminator, researchers take thousands of perfectly written, coherent documents, completely scramble the sentence order into random chaos, and then feed both versions to the AI. The AI's only job is to mathematically discriminate the original, natural order from the scrambled one. By doing this thousands of times, the model essentially teaches itself the invisible glue. It turns sentences into mathematical vectors and learns to calculate the exact coherence score between them all on its own. Which leaves us with a pretty wild question to wrap up this explainer. Today, when a modern AI chatbot writes a flawless, perfectly structured, multi-paragraph essay for you, does it actually understand this invisible glue? Does it know it's using global coherence, discourse connectives, and entity centering? Or is it literally just the world's most sophisticated puzzle solver, mathematically predicting the next most likely piece without ever truly seeing the final picture? The invisible glue of language is something we use effortlessly every time we open our mouths, but teaching a machine to do it is one of the most incredible frontiers in tech today. Next time you read an article, try looking for those invisible connections yourself.